Hello everyone, this is a follow-up example for the previous friction problem, which had the modify Atwood machine, this thing over here. And I will not explain a few things such as the equation for friction, so make sure you watch the previous video. I think it's called friction example, if you haven't done so already. Okay, this one says, a group of students attach a massless string to a 165 wooden block and place it on a surface. The string goes through a modify Atwood machine, frictionless pulley, and a hanging mass of 85 grams is attached to the other end of the string. The modify Atwood machine does not move. Find the acceleration of the system when a 15-gram disc is added to the hanging mass. Assume 85 grams is the maximum hanging mass, which can be attached so that the block does not move. The coefficient of kinetic friction for the block is 0.50. Okay, this problem is a bit more complicated than the previous one because the previous one showed a system which was static. It wasn't moving. In this case, we do have motion. In fact, we have acceleration, right? Because they want us to find acceleration. And let's highlight things which we know are important. We have two masses. I will use green for mass 1. So mass 1 will be the 165 wooden block. And then what else we know about mass 1? Well, then I'll use blue for the other one, the hanging mass. Now you have to be very careful because in this case, our hanging mass is 85 grams plus the 15-gram disc. It'll be a total of 100. And we know the coefficient of kinetic friction is 0.50. That goes with the block. So that goes green. And that's pretty much all we know. And then the acceleration of gravity, that's for both in this case. I'll use yellow for that. Well, it's not here. Well, I thought I had it. It's okay. We know it's 9.8 meters per second squared. So let's write down the given. So given. Whoa. Let's make sure. There you go. Given. We have mass 1, which is 165 grams. Mass 2 is no longer 85, but is 85 plus 15, that is 100 grams. So I'll have 85 grams plus 15 grams. That's a total of 100 grams. That is mass 2. Then we have the coefficient of kinetic friction because now we have motion. So mu's of K, that's kinetic friction. Let's try that K again. 0.50. And we know the acceleration of gravity is 9.8 meters per second squared. And we need to find the acceleration of the system. So A. There you go. Well, let's fix that question mark. There you go. Okay, so let's see what's happening. We are adding a mass here, so that means the system will move. This will pull down on the string. So that means mass 2 will move down, mass 1 will move to the right. We have an acceleration about the pulley, which is clockwise. So the pulley will rotate like this, clockwise. And let me add, so about the pulley, we'll have this type of motion. And let me fix the thickness. Kind of like that, right? That's the acceleration. And for mass 2, we'll have an acceleration down. And for mass 1, we'll have an acceleration to the right. Don't forget that the natural direction of motion, in this case for mass 1 is to the right, and for mass 2 is down. That becomes the positive direction. Okay, and it's based on the clockwise motion about the pulley. So mass 1 moves to the right, mass 2 moves down. Okay. Let's draw our free body diagrams, now that we know what's happening. And I said I would use green, green for mass 1, so I'll use a green box. So green. There you go. Let me just change something here. There you go. Let's add the center of mass. Sorry about that. And let me move this so that we have it elsewhere. And let me state the fact that we are drawing our free body diagrams, as we should, for any forces problem. Free body diagram. And this one is for mass 1. Okay. Yeah, I don't like those. There you go. That's better. We know we have the weight, right? The weight of the mass, of mass 1, which is the force of gravity. Let me fix that arrow. Whoops. Let's fix that arrow. There you go. And then we have, let's label that one. Let's label that one. We have M1. That's an ugly M. M1G. That's the weight of mass 1. And we have the normal force, right? Because this is on a surface, so we have a normal force, which should be equal and opposite, as we don't have any motion up and down for mass 1. Let's make sure, there you go. And normal force, that weird end that we're used to writing now. And then we have the tension for this part of the string, spooling to the right, is at tension. There you go, that's tension force T. And we have friction. In this case, friction is a little smaller than tension because we have acceleration to the right, which means tension is, you can think of winning, right? Tension's winning, so we have acceleration to the right. And there you go. And that's the force of kinetic friction. So friction, kinetic. Now, let's go for mass 2. I said we were going to use blue for that one. Mass 2. There you go. Let me move it to the side. Draw the center of mass. Seems about right. We have the weight of mass 2. There you go. M2G. And we have tension because it's being held by a string. We have tension over here. In this case, tension is a little bit smaller than the weight because we have an acceleration down. We stated that the mass 2 will move down. So therefore, the weight of mass 2 is, you can think of winning. It's unbalanced down. And we know this force up is tension. And there you go. Free body diagrams are done. Next step is sum the forces using our free body diagrams. Let me use purple. So we have the sum of the forces. Let's start with the y direction. The sum of the forces, let's try that again. Sum of the forces along the y for mass 1. And, we need to state which one's positive, which one's negative, right? Well, for mass 1 along the y direction, it really doesn't matter because we don't have motion up and down here for mass 1. So I'll just say this is positive, this one's negative, normal's positive. and then M1G is negative. You could flip it. It makes no difference, truly, because the motion is along the x direction. Now for the x, however, we have motion to the right, so anything to the right will be positive. That means tension is positive, which means force of friction kinetic, negative. For mass 2, well, down is positive because the system, well, at least for mass 2, is moving down, is accelerating down. So this is positive, and this one's negative. There you go. Now we can sum the forces. So along the y, for mass 1, we have the normal force. That one's a positive one, minus m1g. It is not moving, so that's equal to 0. Along the x, so sum of the forces along the x for mass 1, we have the positive force, which is tension, minus kinetic friction. And that is equal to mass 1 times acceleration. We know this side cannot be equal to 0 anymore, because for the last one it was equal to 0 due to the fact that it was a static system. It wasn't moving. In this case, we have motion and we have acceleration. Okay, we have acceleration, so we know this side has to be equal to mass times acceleration because of Newton's second law of motion. Net force equals mass times acceleration. We have an acceleration, therefore we should have a force. Okay. Next, we have, so along the y, for mass 2, sum of forces. Along the y for mass 2, we have the positive weight of mass 2, m2g, minus tension. Again, we have acceleration down. Therefore, this side is equal to mass times acceleration, or mass 2 times acceleration. Okay. I'm going to use the equation for friction. So sum of the forces along the x for mass 1 is equal to tension minus coefficient of kinetic friction times the normal force is equal to mass 1 times acceleration. And we don't know the normal force, but we know what the normal force is based on the sum of the forces along the y direction. So I'm going to move m1g to the right, or I'm going to add m1g to both sides, because I know normal force is equal to m1g. That's the only possibility, so that this system is balanced along the, well, not this system, this mass is balanced along the y direction, right? Because it's not moving up or down. If you look in the y direction, it's not moving, it's just on the surface. It's sliding along the x, but along the y, nothing's happening. So then my equation becomes the sum of the forces along the x for mass 1 is equal to tension minus coefficient of kinetic friction. Instead of normal force, I'll write m1g is equal to m1 times acceleration. Okay, so now I have to focus on these two equations because I'm trying to solve for acceleration. I need to focus on the equations that have acceleration only. So this one here and this one here. We're going to forget about the sum of the forces part. We're going to focus only on this. In fact, I'm going to highlight it. So we're going to focus on this part only for both equations, because we need to make a system of two equations with two unknowns. So let's write it down. We have tension minus coefficient of kinetic friction times n1g is equal to m1 times a. And then we have m2g minus tension is equal to m2 times a. So we don't know tension and we don't know acceleration. We do know g and both masses as well as the coefficient of kinetic friction. Whenever you have a system of two equations with two unknowns, there's many ways to solve it. In this case, I'm going to combine both of my equations because I have positive tension and negative tension. So when I combine them, when I add them up, these are going to cancel, which is very, very convenient. Okay, so let's add it up. Let me add some lines here because I'm not going to be able to draw them straight. You guys know that. Okay. So we'll have tension plus, so tension plus M2G minus all this whole thing, mu K M1G minus tension is equal to, well, I cannot combine these two, so just M1A plus M2A. Very good. Now, this is positive tension, this is negative tension, so they cancel. That's very convenient. So now we have M2G minus coefficient of kinetic friction times M1G is equal to M1A plus M2A. Okay, so now we're going to factor because we don't want two accelerations, we want just one. And we know the acceleration is the same. I should have said that before, right? The acceleration is the same because this is one system and it's connected. These accelerations are the same, okay? This one's the same as this one, We have only one acceleration for the entire system. So now we have, I'm also going to factor the G, so it'll be G times M2 minus mu K M1 is equal to A M1 plus M2. I'm trying to solve for acceleration, so I just divide both sides by all this inside the parentheses, M1 plus M2. It'll cancel. M1 plus M2. So now my equation or formula for acceleration, equation for acceleration looks like this. G times M2 minus mu K M1 divided by the sum of the masses, M1 plus M2. I add parentheses, and that's how I'm going to be able to find the acceleration of the system. Now we just plug in our numbers. So in this case, acceleration is equal to 9.8 meters per second squared. Mass 2, I think that was the 165, right? Oh no, it's 100 grams. Okay, so it'll be, I'm going to add the parentheses at the very end. So 100 grams minus the coefficient of friction kinetic, which is 0.50, times mass 1, which is 165 grams. That was the block. Divided by 100 grams plus 165 grams. Mass 1 plus mass 2. Well, I think I flipped them. It should be 165. Yeah, because mass 1 was... Numerically, it would have been the same, but let's have consistency, right? M1, 165 grams plus 100 grams. I'll use brackets because I already used parentheses. And I do not need to convert to kilograms because I'm going to have this, whatever I get here is going to have the unit of grams. And over here will be, the denominator will be 265 grams. So grams will cancel grams. So if you convert it to kilograms, you get the same answer. So that's why it's not necessary for us to convert to kilograms. Okay, so I'm going to work on this first. Then I'm going to multiply times 9.8. Oh, you know what? No, because the decimals is intelligent, so I can do everything at once. 9.8 times 100 minus another parentheses 0.5 times 165. Then that's divided by, there you go, 265. Let me, well, let me make this full screen because I can't see. And yep, there you go. Our answer is 0.647. I'm going to use 3 decimals to nearest thousandth. 0.647 meters per second squared. Let's go back to OneNote. So in this case, the acceleration of the system will be 0.647. That's an ugly 7. Man, looks the same. Meters per second squared. All right. And that is it.